packet. The last time we met, we talked about the properties of solids, liquids, and gases. Now we're going to talk about the state changes. Okay, so we talked about solids. Sure, I can get this. So solids, or I'll just put solid, liquid, and gas. So we're going to talk about the changes in state from one to another. So probably the most common state change you see on a daily basis is from a solid to a liquid. So that would be melting. Think of ice melting. So that phase change is called melting. What is a liquid going to a solid? What's that called? Freezing. So when you make spaghetti, you boil the water and you kind of feel that moisture around you. That liquid is being converted to a gas once it's boiling. That's vaporization. A gas going to a liquid, the reverse of that is called condensation. So the sweat on your water glass, the moisture in the air is getting cooled and being converted from a gas to a liquid. About this time of year, Halloween time, you think about solid going to a gas. You see those fog machines? That's dry ice. So it's actually cubes or blocks of ice that instead of going from a solid to a liquid, it goes directly from a solid to a gas. So that is called sublimation. So, and I'll put CO2 solid to CO2 gas. This is your fog machine. The reverse of that, a gas going directly to a solid, that's called deposition. So you need to be familiar with all these terms. And if I describe a process to you like ice melting, that would be, saying a solid turns into a liquid, that would be melting, that type of thing. Be able to identify the process. Okay. So the next thing we're going to talk about is the kinetic theory of gases. Yes?
What's an example of deposition?
Deposition.
Is that like if a chemical plant has an explosion or something, and then you get deposits like on your vehicle or something from it? I don't know, I'm only saying that because we had that in New Orleans once.
Possibly.
It doesn't happen very.
Does not happen very often.
Okay.
I will look up an example for you. So, I'll write that down. Let's talk about gases now. We are going to get into our gas law section. And, if you take Chem 1 or you take a higher level of chemistry, the gas law section is very big, complex. You do calculations, you use PV equals nRT, all this. We do not get into it. All we talk about is the relationships between different properties of gases. And before we get into those relationships, we need to cover the assumptions about gases. So that's what the kinetic theory of gases is. So the kinetic theory of gases is a group of assumptions that explains gas behavior. So the first assumption is kind of just a description of what a gas is. This is kind of a review of that table. A gas is made up of small particles moving randomly with no attractive forces between them. So small particles moving randomly with no attractive forces between them. The second assumption is that the particles are very far apart. So I had this friend when I was going through chemistry undergrad, and she would always think of these crazy things, you know, like I can remember talking specifically about solids, liquids, and gases. And she would liken them to people she knew. She'd say, oh, a gas. You know, those are the people that don't want to be near anybody. They want their space. They're not the touchy type of people, you know, and then she would go into great detail about, oh, I think I'm more of a liquid, and these things. But she was always a very good student because she remembered these things, you know, even though it was crazy, and I kind of look at her and say, Molly, how do you come up with these things? She always did very well. So if you can think of that, and it seems like a lot of you already do that, it makes it more memorable and kind of humorous at times. So, okay, the third assumption, particles, and all of these particles that we're talking about are gas particles. Particles move faster at higher temperatures. And the last assumption is that collisions between particles are elastic. So collisions are elastic. What does elastic mean? Well, you know the elastic waistband, you know that you. Not that. Elastic collisions means that kinetic energy is conserved. Conserved, yes. So KE stands for kinetic energy. Kinetic energy is conserved. And when you measure, like the tire pressure in your tires, that pressure is a result of the collisions between particles. So pressure is a result of collisions. So what would you expect? A tire pressure. And so would you expect a change in tire pressure from summer to winter? Yes. So, in the summer, what do you know about the temperature? Yeah, so you have higher temperature, more collisions. Because there are more collisions, you're going to have higher pressure.
I don't know if this is true, but I've heard like when you're getting gas at the gas station that you, besides the atmosphere, reason for, or the ozone alerts that they give, that pumping in the morning, you tend to get, it might not be a lot, but you get more gas than you would if it was hot. Is
Yes,
that true?
that is very true. So so when you hear the advice to get gas in the morning as opposed to the afternoon, that has to do with the volatility. And that phase change is liquid to a gas, right? So that vaporization. So when it's hotter, you're going to have more of it going, and it's confusing because you talk about gas, but you're really talking about gasoline, which is a liquid that you pump into your car. So when you pump that into your car and the temperature is lower, you get more in the liquid form as opposed to the gas form. Now, sometimes when it's really hot and you're pumping your gas, you can see the vapors rising. So you're paying for that gas, but it's not going into your gas tank. So,
Is that why some of the gas stations have that, like a rubber thing that goes around your?
yes, trying to get the best CO possible so that you're keeping the temperature of that gas as cool as possible, opposed to warming it up. And we'll talk about this more too when we reach organic chemistry. But gasoline is an organic compound. Organic compounds by nature are highly volatile. And that means they go from a liquid to a gas very readily. It doesn't take much, just a little increase. If you think about perfume, that's something that you want to be volatile so you can smell it. And if you think about gasoline, you can definitely smell gasoline very readily. Yeah, good question. All right, gases are described by 4 properties. These properties are pressure, so I'll put P for pressure, volume, so I'll write pressure, volume, lowercase n, that stands for molar amount, and then capital T for temperature. We're going to go on to the next page and do some calculations involving pressure. So, the definition of pressure, remember we talked about it's the collisions that cause the pressure. Pressure is defined as force per unit area. And it's not that you will have to use that equation any, but knowing another definition for it, aside from the collisions. The units for pressure that we will see, atmosphere, ATM, millimeter of mercury, or torricelli. So these are the units that we'll use in this class. Just to give you an idea of what an atmosphere is, the atmospheric pressure at sea level is 1 atmosphere. Does anybody know what happens as you go higher and higher in altitude? What happens to atmospheric pressure? It drops. Yes, it drops. So there's less oxygen in the air. So that's why when you go running in Colorado and you're very high up, you're like,
Your body has to produce more red blood cells while
Right.
Olympians go do the doping thing that they
right.
talk about.
Yeah, so you don't have as much oxygen because the atmospheric pressure is lower. Now, the other units of pressure, millimeters of mercury, torricelli, you'll see these units in blood pressure readings. And if you look at the old sphygmomanometers, right, you'll see the units, it will have torr or mmHg. And when you look, mmHg, it looks kind of funny, but that really that's the abbreviation for millimeter. And then what's the symbol for mercury? Hg. So that's how they come up with that. Now, there are two conversions that you need to memorize. Absolutely have to memorize. And I have them in this box. Know these for the exam. You will not be given these. 1 atmosphere is 760 millimeters of mercury. 1 torr is the same as 1 millimeter of mercury. So you could expect to see a question like this one. The pressure on a jet airliner is 22 centimeters of mercury. How many atmospheres is this? How many torr is this? So just like all your other conversion problems, you're going to write out your starting quantity. And if you want to have a conversion roadmap, that's helpful. So centimeters of mercury, we're going to have to convert that to millimeters of mercury. And millimeters of mercury we can get to torr, so you can stop right there because that's 1. In order to get to atmospheres, you can write out another one. Or you could go torr to atmospheres too, because you know that 1 torr is 1 millimeter of mercury. Okay, so centimeters of mercury to millimeters of mercury. It's been a while since you saw the conversion, the prefix conversion ladder, but keep it fresh in your head. So you have mega, kilo, base unit, deci, centi, milli, micro, nano. So that's 6, 3, 1, 2, 3, 6, 9. So in 1 centimeter of mercury, how many millimeters of mercury are there? So you're just going from 2 to 3. You're just going 1 to the right. So it's 10 millimeters of mercury. So 22 times 10, and if we do this, 1 millimeter of mercury is equal to 1 torr. If you stop there, 22 times 10, you'll get 220 torr. That's one answer. So you can also extend this other conversion. 1 atmosphere is 760 millimeters of mercury. It's also how many torr? 760. So how many sig figs? 2. So it comes out to be 0.28 ATM. So on, oh, did I? Oh, yeah, I didn't remember. Thank you. So this would be, sorry, 0.29. If you look at my calculator, you can see we're not. Okay, so this 8 will get rounded up by that 9, so it would be 0.29 atmospheres. Thank you. So for sure, memorize these conversions. You will not be doing those. On the next page, I have 2 more questions. And go ahead and work the first one. This second one, convert the systolic and diastolic blood pressures separately. So 150. So convert those separately.